So we have defined inside affine schemes what it means to be an open and a closed set. And then for affine varieties, we had seen that there's particularly nice open sets, which were these distinguished open affine sets, which are the complement of the vanishing locus of a single element of the coordinate ring. And we do the same thing for the affine schemes. So we define the distinguished open subsets just if R is a ring and F is any element. Then we define D of F just as before the complement of the vanishing locus of F. And if we spell it out, the vanishing locus, this was the set of prime ideals of R containing the ideal generated by F. So in other words, containing F. And so if we remove it, then we just get the prime ideals which don't contain F. And this is called the distinguished open subset of F. And if we make the comparison, now we can kind of compare all the notions that we had seen before, just for X being an affine variety of an algebraically closed field. Then we had seen that the points A in X correspond inside the spectrum of the coordinate ring to the maximal ideal MA, which is just the ideal of all functions vanishing at A. And we have seen that this is an injection. We can uniquely recover A from this maximal ideal, for example, by taking the vanishing locus. So this shows that this big phi is an injective function. And moreover, we have seen the prime ideals in AX, they're not necessarily closed. If you take the closure, you just get all the prime ideals containing P. And so the closed points are exactly the maximal ideals. And so somehow this is an injection, and its image is just a set of all points in the spectrum which are closed in the Zariski topology. And moreover, this doesn't just work well on the level of sets, but also it respects the topology. So if you, for example, take the pre-image of the vanishing locus of J in the spectrum sense, then, well, this vanishing locus, this is the set of prime ideals containing J. And so here we get the set of points A such that MA contains J. And then if you take this inclusion and apply the vanishing locus on both sides, you get that A is contained in the vanishing locus of J. And this is an if and only if by the classical Nullstellensatz. And so here you just get the A in X such that A is contained in the vanishing locus of J, which is just the vanishing locus of J. So we see, take the preimage of the scheme theoretic vanishing locus, you get the usual vanishing locus. This works for all ideals. And in particular, if you take the preimage of D of F, then it's the A in X such that this is not contained, F is not contained in MA. In other words, F does not vanish at point A. This was exactly the definition of the usual D of F before. So this property here that it respects the Zariski topology shows that this is an injection and it's a homeomorphism onto its image. So in this weird scheme theoretic object spec A, X, you have a copy of X sitting inside, even as a topological space. So you just added some extra stuff. Okay, so this was this comparison. And then we have seen the nice thing about the distinguished open sets was that they form a basis of the topology. And this still works, because if U in spec R is open, then in other words, it's the complement of some Zariski closed set, so some vanishing locus. And then so you write it like this: spec R minus the vanishing locus, and the vanishing locus, this is a set of prime ideals containing all of the elements of S. And so if you can write it like this, or you can write it just as an intersection of all these vanishing loci, because these are the prime ideals containing F, and if you take the intersection, then you require that they contain the entire set S. But then spec R minus this intersection, this is just basic set theory, is the same thing as the union of spec R minus each entry, and this is D of F. So what this small calculation just shows is that any open subset is a union of set D of F, like this. So this is a basis of the Zariski topology. One word of warning here, for the affine varieties, it was true that any open set is actually the union of finitely many D of Fi. And this came from the fact that the ring R was Noetherian, and so this kind of ideal, if you take S to be a full ideal, and this is generated by finitely many Fi. This is no longer the case for arbitrary schemes. So here one has to be a bit careful. You can still write any open set as an arbitrary union of D of Fi, but not necessarily as a finite union. Okay. And so later in further videos, we're going to study these D of F and then also study what are the functions on those. And for this, we had, if you go back to the affine variety treatment, we had a useful lemma. And we just want to have the scheme theoretic version now, because it makes the proof there a bit easier. And this is this partition of unity argument, which says that if D of F is some union of D of Fi, for I in some index set, then, and here this is important, we do find a finite subindex set I0 in I, and coefficient elements Ri and R on this finite index set, such that we can write some power of F, the big, the thing for the big set here, as such a combination of Ri times Fi in R. And the idea, why was this called partition of unity? Well, we're going to see that this function f to the m is a unity, or is a unit in the ring of functions here. And so you write this unit as a finite sum of things. Okay. And the proof is really not hard. It fits in these few lines, because now you say this star, what does it just mean? If you take the complement on both sides, then you can write V of F as an intersection. The complement switches the union to an intersection of the vanishing locus of all the Fi, which is just the same thing as the vanishing locus of this ideal generated by all of them. Okay, and then, so we have now V of F is equal to V of this ideal here, and then by the Nullstellensatz, if you apply the ideal function on both sides, then you get the ideal of the vanishing locus of F, but this by the Nullstellensatz is just the radical of this ideal here is equal to the radical of the ideal on the other side. Here we just apply the kind of like I on both sides. And well, F is of course contained in the radical of its own ideal, because F to the 1 is contained in here. And so spelling this out, what does it mean that F is in this in the right-hand side ideal? It just means that there exists an M such that F to the M is in this ideal here. And well, this already finishes the proof, because this thing being contained in here means, and that's where the finiteness comes in, that this is a finite combination of these Fi times Ri. And so we can indeed conclude the lemma. And this will be useful when we calculate the ring of regular functions on this D of F.